Hi, it's Mrs. Mafucci, and it's time to review gases and the gas laws. This is part 2 of a two-part series. Let's consider the following problem involving Dalton's law of partial pressure. We have a sample of natural gas which contains 8.24 moles of methane, 0.421 moles of ethane, and 0.116 moles of propane. Now, if the total pressure of the gases is 1.37 atmospheres, what is the partial pressure of propane? Well, in order to solve this problem, we need to know the following formula. P sub I is equal to chi sub I times P total. What this means is that the partial pressure of I is equal to the mole fraction of I times the total pressure. Now in this problem, I gave you that the total pressure was equal to 1.37 atmospheres. So now all we have to do is determine the mole fraction of the propane. Mole fraction is equal to number of moles of propane over the total number of moles of gas. Then we're going to take this, change it to a decimal, and then we're going to multiply it by the total pressure to give us a partial pressure of 0.0181 atmospheres. Now, for this problem, I changed mole fraction to a decimal. You don't have to. You can leave it as a fraction. In the next problem, I am going to leave it as a fraction. In this problem, we have a total pressure of a mixture made up of 3 moles of helium and 4 moles of neon. The total pressure is 97.4 kilopascals. Now we want to find the partial pressure of each gas. Remember, according to our previous equation, partial pressure is equal to the mole fraction times the total pressure. So for this problem, we have a mole fraction of 3/7 for helium times the total pressure of 97.4 kilopascals to give us a partial pressure of 41.7 kilopascals. For neon, we're going to have 4 divided by 7 times 97.4 again to give us a partial pressure of 55.7 kilopascals. Now you should realize that if you add the partial pressures of a mixture of gases, that should equal the total pressure. So the partial pressure of helium plus the partial pressure of neon should equal the total pressure, 97.4 kilopascals. Now let's look at the gas laws. Now the gas laws are used to describe the behavior of gases, and we're going to consider the factors important for the gas laws. We're going to consider pressure, we're going to consider volume, we're going to consider absolute temperature, and we're going to consider number of moles of gas. Now we're going to look at the relationships between these measurements before we look at the specific laws. Remember, pressure can be in atmospheres, millimeters of mercury, torr, or kilopascals. Volume can be in liters, milliliters, or cubic centimeters, but temperature always has to be in Kelvin. Now the relationship between number of moles and pressure is this. As the number of moles increases, the pressure increases. Now this is assuming that volume and temperature are constant. What about the relationship between temperature and gas pressure? Well, as temperature increases, gas pressure increases. Again, we're assuming a constant volume and a constant number of moles. In our next relationship, we're looking at volume and gas pressure. Now, these two things are inversely related to one another. That means that if I decrease the volume, the pressure is going to increase. Again, assuming that temperature and number of moles is constant. What about the relationship between temperature and volume? Well, as temperature increases, volume increases at constant pressure and number of moles. And finally, the relationship between number of moles and volume. If I increase the number of moles of gas, I'm going to increase my volume at constant temperature and pressure. Now, let's take a look at Boyle's law. Boyle's law is the relationship between pressure and volume. We can see from this graph that as we increase the pressure, the volume goes down. It is an indirect relationship. Now let's consider this problem. If 1 liter of a gas originally at 100 millimeters of mercury has its pressure increased to 200 millimeters of mercury at constant temperature, what is its new volume? Well, we want to use Boyle's law. P1 times V1 equals P2 times V2. Don't you see that I'm doubling the pressure? That means I'm squeezing the gases into a smaller volume. It should make sense to you that if I double the pressure, I'm going to halve the volume, which we can see from this diagram. When I doubled the pressure, the volume was halved. P1 times V1 equals P2 times V2. Now this is a graph of Charles's law. Charles's law is the study of the relationship between temperature and volume. And as temperature increases, volume increases. If you look at this graph, notice the temperature is in Kelvin. Remember, we always want to do it in the absolute temperature scale. Notice also that when the temperature is at absolute zero, kinetic energy is zero, there is no volume. When absolute temperature is zero, volume is zero. Let's consider this problem. If 50 milliliters of a gas originally at 500 Kelvin has its temperature increased to 1000 Kelvin at constant pressure, what is its new volume? We're going to plug this information into the formula V1 over T1 equals V2 over T2. Remember, temperature must be in Kelvin. Now, if you look at this problem, don't you see that the temperature is being doubled? If I double the temperature, I'm going to definitely double the volume. This graph shows that very thing. Originally, the sample was at 500 Kelvin, and it occupied a volume of 50 milliliters. When I doubled the temperature to 1000 Kelvin, the volume was also doubled to 100 milliliters. The last relationship is Gay-Lussac's law, the relationship between pressure and temperature. As pressure increases, temperature increases, and vice versa. In this graph, the temperature is on the bottom in Kelvin and the pressure is on the vertical axis in atmospheres. Notice that when I double the temperature from 500 to 1000 Kelvin, I double the pressure from 10 atmospheres to 20 atmospheres. P1 over T1 is equal to P2 over T2. That's Gay-Lussac's law. And remember, temperature must be in Kelvin. Now this is a summary of the gas laws. Boyle's law, PV equals PV at constant temperature and number of moles. Charles's law, V over T equals V over T at constant pressure and constant number of moles. And Gay-Lussac's law, P over T equals P over T at constant volume and constant number of moles. We want to now consider the ideal gas law. PV equals nRT. P is pressure in atmospheres, V is volume in liters, N is number of moles, R is the ideal gas constant, which I will always give to you on a test. We're going to assume that the ideal gas constant is 0.0821 liter atmospheres per Kelvin mole. T is temperature in Kelvin. We're now going to solve a problem using the ideal gas law. Now, you may want to pause the video right now so you can copy down this problem, solve it, and then continue as I go over the answers. question A, I wanted to find the number of moles of helium. Moles of helium is 24 grams times 1 mole over 4 grams of helium. Remember, helium has an atomic weight of 4. So I have 6 moles of helium. Now in my next problem, I wanted to know how many moles was 42 grams of nitrogen. What you have to remember is that nitrogen is a diatomic. Don't forget your diatomic elements, H2, N2, O2, F2, Cl2. You have to remember that if you're going to change grams to moles appropriately. 42 grams of nitrogen is 1.5 moles of nitrogen. Now, we want to know the mole fraction. For helium, it's going to be 6 over 7.5. For nitrogen, it's going to be 1.5 over 7.5. So now, how are we going to find the partial pressure of helium when I didn't even give you the total pressure? Well, now we can use PV equals nRT. I plug in my volume, 250, is equal to my number of moles, 6, times the ideal gas constant, 0.0821, times a temperature of 298 to give me a partial pressure of helium of 0.587. We're going to do the same procedure to find the pressure of nitrogen. P times 250 is equal to 1.5 moles of nitrogen times 0.0821 times 298 Kelvin. In this case, nitrogen has a partial pressure of 0.147 atmospheres. Now remember, if I want to find the pressure, all I have to do is add up the partial pressures. The last problem involved changing volume of this gas to STP conditions. Now when I plug in STP conditions, my pressure is 1, my volume is my unknown, my number of moles is 7.5, my ideal gas constant is still 0.0821, but now my temperature is standard temperature, which is 273. So when I change this gas that was originally at 250 liters, it changes to 156.9 liters when this gas sample is at STP. We're going to look at one more problem. If 5 moles of helium are in a container with 9 moles of argon, what is the partial pressure of argon if the partial pressure of helium is 790 millimeters of mercury? Well, we have to remember our formula from before, that the partial pressure of helium is equal to the mole fraction of helium times the total pressure. Well, I know the partial pressure is 790. I know the mole fraction is 5/14, so I can use algebra and determine that the total pressure is 2212 millimeters of mercury. I can now use this total pressure to determine the partial pressure of argon using the same formula. But this time my mole fraction is going to be 9/14 times the total pressure, which I calculated just previously. Multiply them two together and I'm going to get 1422 millimeters of mercury.